Hello and welcome back everyone. This is semester 2, academic session 24-25, and I'd like to introduce you to our course today, Radiobiology and Radiation Chemistry. This is supposed to be registered under elective, so make sure that you get the registration code right. So it is under E, and this course is a 2-unit course, and the lecture time supposedly to be on every Wednesday at 11 a.m. to 11:50 a.m. And we'll have a 10 minutes break for another 50 minutes second from 12 to 12:50 p.m. And the location of the venue would be at BT 161. The venue would be close to where we had our class last semester. So in this course, we will be doing or we'll be focusing on number one, to identify biological effects. So basically, we want to try to understand the biological effects caused by ionizing radiation, specifically or more focus into the biological effects that is a concern in radiation therapy and planning. Next, we have principle of radiation chemistry. We will be exploring the principles in radiation chemistry and their impact on our biological system. Again, this is specifically designed for radiation treatment and planning. And we also will be doing some sort of verification of concepts. So we'll be applying of concept or the concepts of radiobiology and radiation chemistry to solve real world biological problems and critical thinking assignments, things like that. So that's what we will be doing in this semester. So these assessments, this course will be assessed based on three modes. One is the coursework. The coursework is 50%, means that we have 20% comes out from test and another 30% comes out from your assignment. And we will also have final examination, so that's another 50%. So we will be doing, I will detail out all the assessment structure when we meet for the first time during the face-to-face session after it or yeah, is over. All right, so this is topic one. So what will be covered? This is topic one, introduction to radiobiology. But what are other topics? Other topics include the first one is introduction to radiobiology. Second, cell survival curves. Third, the radiation chemistry. Fourth, dose, time, and fractionation. This is in regard to radiation therapy. Fifth is biological effects of radiation. This is mainly about the targeted radiotherapy planning and treatment, and also the radiation protection effect of it. So there are six altogether. Introduction, cell survival curves, radiation chemistry, dose time fractionation, biological effects of radiation, and finally radiation protection. So throughout the class, I encourage you to actively participate in the class and throughout the course so that we can have a fun learning session. Well, I hope to have fun with you guys. I'm not sure if you guys are going to be having fun with me. One second. All right. All right. Now, what is radiobiology? Radiobiology is a branch of science that combines the basic principle of physics and biology. So basically, it is an interdisciplinary field. It merges the two concepts, which is physics and biology. So in this course particularly, we are going to investigate the effects of ionizing radiation and the target biological tissues and living organisms in under the radiotherapy treatment planning concept. So that's what we're looking at in this course. But in general, what is radiobiology? It is a field of study that focuses on understanding how ionizing radiation affects living tissues. If you're undergoing a radiation therapy treatment, obviously you are a living organism. So living tissues and organisms. So what are the key things in this paper or in this course? To investigate the effects of ionizing radiation, to study how radiation interacts with biological tissue and living things, and finally to study the effect of the changes caused by the radiation absorption. Is this 1 second? All right. Now, although we have done this in 532 when we did radiation physics together, we'll do, well, this is a quick revision. So what is ionizing radiation? What are the different types? What are the sources? So basically, the type of ionizing radiations that we have all been introduced to in the last semester on the 532, they are X-rays, gamma rays, alpha particles, beta particles, neutrons, and etc. So what are the sources? Uh, there are many different type of sources you can have from cosmic radiation, natural background, from the medical imaging or therapy modalities, from the nuclear industry, from the research, scientific research, and so on. So there are many different sources, but of course, this course is tailored to the um, machine or the non-natural ionizing radiation. So now, what are the biological effects that we are looking at in this course? Number one is cellular damage. So what are those? For example, DNA breaks and mutation. Next, we have chromosome aberration, so that it goes also under cellular damage. After that, we have molecular alteration. So this means that it goes further up to damage the protein and lipids at the cellular level. So this cause the series generation of reactive oxygen species. And finally, tissue and organs respond. So it could be inflammation, fibrosis, necrosis, apoptosis. So those are the kind of things that we'll be looking at in this course. So basically, we are doing or we're looking into how ionizing radiation can directly damage cells and DNA, leading to mutations and chromosome changes. It might also cause molecular alterations such as damage to the proteins and lipid and the generations or the production of reactive oxygen species. So these cellular and molecular effects can manifest into a further uh, damage into tissue and organ level. This includes fibrosis, inflammation, cell death, and so on. So why do we need to study this? Understanding this biological exposure is important so that we understand the risk and the impact of ionizing radiation, regardless for medical or in this course for medical purposes, but in general for industrial or other purposes of ionizing radiation utilization. So by breaking down different types of ionizing radiation, the corresponding biological effects at the cellular, molecular, and tissue organ, uh, we can understand or we can develop a comprehensive understanding of this important topic in radiation biology and health physics. All right, let us continue to this topic because I was trying to fix the microphone earlier. All right, so basically the basics of this course is understanding radiobiology. So in radiobiology, we'll be studying how ionizing radiation affects living tissues and organisms. And finally, we are going to combine the principles of physics and radiobiology to understand these effects. So basically, it is the combination of two fields of studies. So what are the key mechanisms in radiobiology? Number one, there must be ionizing radiation and energy absorption coming from this ionizing radiation. So we have the how radiation, so we are going to have a look how radiation interacts with living tissues and how the energy is basically deposited. Next, we are going to have a look at the cell structure impacts, how radiation affects cell membranes, the organelles, and the nucleus, and what is the subsequent repair processes that will take place after the energy absorptions and manifestations. So, how the cells try to fix radiation-induced damage at the cell cycle, different cell cycle phases, and so on. So we are also going to have a look at the factors influencing radiation effects, radiation quality, the type of radiation, and the energy, its energy transfer. We are going to have a look at the LET, RBE of different ionizing radiation. Next, we're gonna be looking at the dose rate, whether exposure is acute or chronic, and the role of fractionation, how it takes place, especially how it's helping or not helping radiation therapy planning or the treatment of treating cancer using ionizing radiation. And then we are going to have a look at the oxygen effect, how oxygen levels, OER, and tumor hypoxia, which is the tumor that has been suffocated from lack of oxygen, impact radiation response in your typical um, radiation treatment and planning. So this is basically what the course is in a bit more detail. So what are the applications of radiobiology? So one of the obvious application of radiobiology is in the field of cancer radiotherapy itself. How we're going to maximize the control of tumor cells and minimizing damage to the healthy surrounding tissues. So the first application of radiobiology is in the cancer radiotherapy management itself. Secondly, we have to understand radiobiology for the purpose of understanding radiation protection. So we're going to establish safety standard for occupational and radiation exposure. So we are going to understand how public health protection and measures together with environmental protection are measures and developed to protect users and environment from the hazardous ionizing radiation. And of course, there are other usage of radiobiology that we will not be looking at, but worth to be mentioned. We can, for space exploration, for example, we can, based on the understanding and knowledge in radiobiology, we can understand the risk of cosmic radiations, cosmic radiation for astronauts. So, and the understanding of radiobiology can design a better protective strategies for long duration space mission. I'm sure that we all are aware. Recently, the two astronauts that were supposed, there were 8 astronauts. I can't remember, but they were astronauts sent for 8 days mission ended up being to 236 days or something mission. So understanding radiobiology will actually give a better protective strategy for long duration space mission, especially for the astronauts. All right, let's do a little bit of revision together. What are the different types of ionizing radiation? Number one, we would have gamma, beta, alpha, Auger electrons. So these are, of course, there are many more. You have all these neutron, you have beta positive, beta negative, and so on, X-rays. But these gamma and X-rays, basically they interact with matters the same way. So when I say gamma, it also applies for X-rays. Although the source are different, gamma is from radionuclide, but X-ray is from machine or from the LINAC, linear accelerator, or your conventional X-ray machine. But the way how gamma and X-ray interacts are the same. So regardless, gamma and X-ray, you have beta, and then you have alpha particles and Auger electron. So gamma radiation basically is a moving high energy electromagnetic radiation. It can penetrate deep into materials and it requires shielding to protect against the exposure. So in the context of radiotherapy, cancer radiotherapy, we want to protect the healthy tissue adjacent or located close by to the targeted tissue. So it is extensively used in medical imaging and cancer treatment. Next, we have beta. It's basically a fast-moving electrons or positrons. It can be stopped by heavy materials and can cause damage to living tissue, often emitted in a nuclear reaction or unstable nucleus that is decayed to reach stability. Next, you have alpha particles. It consists of two protons and two neutrons. It is a lot heavier, slower than beta particles, and it can be easily stopped by a sheet of paper or just the dead skin layer of your body. It's easily stopped. And next you have OG electron. So OG electron basically is ejected from an atom when inner shell electron is removed. So it can cause damage again to the biological tissue, and this is not really this OG electron is not used for treatment mainly, but it is a concern because OG electron is produced and cause radiation absorbed dose to your patient when when radiation is used to treat cancer patients. So basically, these are the type of different ionizing radiation that we'll be looking at in this paper. So as I said earlier, so we have gamma. So gamma produced by the subatomic particles interaction, obviously most importantly during radioactive decay. So typically the energy of gamma is more than 25 keV, and it travels like wave-like particles. So if you still remember your first year course, if you did physics, which is ZCT104, so it travels as wave-like particles at the speed of light. It has no mass and electric charge that allows it to penetrate deep into materials and commonly emitted when there is a radioactive decay process. So that's gamma to you. All right, so this gamma radiation is a form of electromagnetic radiation that occurs during various nuclear or various radioactive decays. So when gamma interacts with matter, in our case, in with your patient, it can undergo several types of interaction. These include photoelectric, Compton, and pair production event. So this interaction results in the creation of secondary particles, usually electrons or photons with reduced energy that would be a concern to the localized absorbed dose to the patient. So here basically the secondary electrons are the most in concern because these are produced during the initial interactions by the gamma radiation. So it creates secondary electron close to the site where this ionizing radiation or the gamma radiation is focused in. Next, the production of secondary photons. So the secondary photons carry energy further away from the initial interaction. So following the subsequent electron production interaction, these photons are responsible for dose deposition at a distant site. So if you have a localized target, all right, Ben. All right, you have a segment and this is your localized target. Secondary electron will be created here, but secondary photon will be created further away, and maybe over here, these are where all your surrounding healthy tissues. So that would actually produce a further concern because the dose deposited here is not is unwanted. So this is where your healthy tissue is, for example. So that would be concerned that things that we'll be looking at in this paper. Next, you have beta. Beta is a type of ionizing radiation emitted as a consequence of radioactive decay, specifically when there is a relative excess of neutrons for beta negative or protons for beta positive or positron in the nucleus of a radioactive atom. So the key points about beta that we should take note of, number one, in a beta minus decay, neutron in the nucleus is converted into proton, and this process emits an electron and antineutrino. Next, you have beta plus or positron, a proton in the nucleus is converted into a neutron, and this process emits a positron and antimatter part or counterpart of an electron, and it also emits a neutrino. So what is the energy or spectrum of a beta? So the energy emitted by beta particle is very important to be considered. So the beta spectrum determines how the beta particles can penetrate living tissue and the amount of energy that will be deposited in that tissue. This can have a significant biological consequences. So if you remember what we did in radiation physics, we would you have already seen the beta track where it goes everywhere and so on. It is not easily predicted in comparison to your gamma track. So what are the characteristics of beta radiation? It consists of fast-moving electrons or positron. It can be stopped by heavy materials. It can or dense material. Beta radiation can cause damage to living tissues as the energy deposition can disrupt at a cellular level. So this radiation is often emitted in nuclear reactions and radioactive decay, and this will then, if you have heard of brachytherapy and significant other other significant application of beta in cancer treatment, so it's something like that. So we are going to have a look at that as well. Okay, now radionuclides that emit both beta particles, some of the radionuclides, they emit both beta particles and gamma. So the particulate radiation and the photons. So for radionuclides that emit beta and gamma at the same time, usually the beta delivers greatest fraction in that emission compared to the photons. For example, you have iodine 131 for thyroid treatment. About 90% of the radiation dose delivered to the thyroid gland from iodine 131 is from beta, not from gamma. So the beta emissions contribute more significantly to the overall whole body dose compared to gamma emissions. So what is the important keys here? So the particulate radiation from radionuclides that emit both beta and gamma tends to deliver beta as the greatest fraction of the total radiation dose to the specific organ, and this must be tallied accordingly when planning for the treatment of your particular subject or patient. So, important consideration in understanding the potential biological effects in internal radioactive contamination and absorption, and must be studied and planned, and the localized beta radiation dose to the affected organ can be much higher compared to the overall whole body dose. So that's beta coming from radionuclides that emit both gamma and beta at the same time. Next, we have alpha particles. Alpha particles are emitted when heavy and unstable nuclides undergo decay. So they consist of helium nucleus with 2 protons and 2 neutrons emitted in a nuclear decay. So these particles give up their energy within a very short range, typically less than 100 micron. So they are emitted from nucleus of certain types of unstable atoms during alpha decay. And these alpha particles usually have high energy range in MeV levels. So they lose their energy in a very short range, making them biologically very effective. And as they have to treat small size cancer tissue, and they possess a high linear energy, or we call them as a high linear energy transfer ionizing particles. So there are many different applications else than medical. So they're used in smoke detector, for example, and a certain type of cancer therapy in certain types of cancer therapy utilizing alpha emitting radionuclides, where they are used to specifically target and destroy cancer cells while minimizing damage to the surrounding healthy tissue. Because the range is small, we would be able, so for example, you have tissue, all right, you have a tissue and this is your target area. Because alpha particles only travel within a short distance, now the surrounding healthy tissue can be preserved. So certain types of alpha emitting radionuclides can be used to treat targeted cancer due to its high energy, high LET properties. Of course, alpha particles have other uses, for example, in research, to investigate atomic nuclei, and so on, many different applications. Okay, and finally, we have OG electrons. So OG electrons are emitted by radionuclides that undergo electron capture or internal conversion. So this decay process leaves the atom in a highly excited state with a vacancy in one of the inner shell. So when there is a filling of this vacancy, so you see here, the vacancy in the inner shell is then rapidly filled by either through a fluorescent transition, through the emission of characteristic radiation, or by non-radiative OJ transition. So the energy gained by the electron transition to this further in or the deeper orbital is used to eject another electron, and this electron, so this electron is termed as OG electron. So OG electrons are basically short range, low energy particles that is often emitted in the form of cascade. So this consequence of inner shell atomic vacancy transversing up through the outermost orbital. So this will create OG electron, and and then it'll be further up, there'll be more OG electron with lesser energy emitted out of this atom. The cluster of very low energy OG electrons can produce ionizing densities comparable to those produced in alpha particle track. So that is the direct comparison. So the radionuclides that decay by electron capture or internal conversion can exhibit high LET-like behavior close to the site of the decay. So it's comparable to alpha high LET, so that we consider it as it has high LET behavior. So this high LET behavior can significantly um, affect the biological effects in medical imaging, radiation therapy, and nuclear physics, and so on.